Hello everyone, my name's Iman. Welcome back to my YouTube channel. Today, we're diving into electronegativity and how it determines bonding. We're going to classify bonds as covalent or ionic. We're going to explore bond polarity, and we're going to learn how to name ionic compounds. Finally, we'll introduce lattice energy to understand the stability of ionic structures. Let's go ahead and get started. To understand bonding, we first need to talk about electronegativity. Electronegativity is the ability of an atom to attract electrons in a chemical bond. Electronegativity increases across a period from left to right. This is because elements on the right side of the periodic table, particularly nonmetals, have a higher effective nuclear charge, meaning they exert a stronger pull on electrons. In addition, electronegativity decreases down a group as you move from top to bottom. This happens because atomic size increases, meaning the valence electrons are farther away from the nucleus and they experience more shielding, and that's going to reduce the nucleus's ability to attract bonding electrons. Because atoms differ in their electronegativity, the difference in electronegativity between two bonded atoms determines how the electrons are distributed in the bond. For this reason, it's super important to memorize the following electronegativity values seen in this table. Now, if the electronegativity difference is small, less than 1.7, then the bond is considered covalent, meaning electrons are shared between the atoms. If the difference is greater than 1.7, then the bond is considered ionic, meaning one atom takes the electron completely. This distinction allows us to classify bonds based on their difference in electronegativity values. Within covalent bonding, we need to distinguish between nonpolar and polar covalent bonds. For this course, we're going to keep it simple and general. A nonpolar covalent bond occurs when two atoms share electrons equally, meaning there's no significant charge separation within the bond. This happens when the bonded atoms have similar or identical electronegativities. One prime example is diatomic molecules like H2 or O2 or C2 or N2. The electronegativity difference in these bonded atoms is equal to 0, so they are all nonpolar covalent bonds. A polar covalent bond, on the other hand, occurs when two atoms share electrons unequally, and that causes one atom to pull the electrons closer to itself, creating a partial charge separation. The important takeaway for polar covalent bonds is that as the difference in electronegativity increases within the covalent range, so up to 1.7, the bond becomes increasingly polar. Allow me to repeat. The degree of polarity in a bond depends on the electronegativity difference between the two atoms. As the difference in electronegativity increases, then the bond becomes more polar. And that means that there is a charge separation between the atoms that becomes more pronounced. This charge separation is what creates a dipole. This is simply a difference in charge across the bond, where one atom becomes partially negative and the other becomes partially positive. One example of a polar bond is a carbon-fluorine bond. Fluorine is much more electronegative than carbon, so it pulls the electrons a little bit closer to itself. Now, the closer the difference in electronegativity gets to the 1.7 threshold, then the stronger the dipole becomes, meaning the electrons are now pulled more unevenly between the two atoms. But if the electronegativity difference exceeds 1.7, then the bond is no longer polar covalent. It is ionic, meaning the more electronegative atom completely removes the electron from the other atom, forming charged ions instead of a shared electron pair. Now, while individual bonds can be polar, that does not necessarily mean that the entire molecule is polar. So if we were to look at something like carbon bonded to 4 fluorine atoms, the individual carbon-fluorine bond is in fact polar. However, the dipoles for all 4 of these bonds in the molecule cancel out, so this molecule as a whole is actually nonpolar. Molecular polarity, it depends on both bond polarity and molecular shape. So this concept will make more sense when we come back to it in a later lecture. But keep that in mind. Individual bonds can be polar, but that does not necessarily mean that the entire molecule is polar. So these concepts, electronegativity, covalent and ionic bonding, and bond polarity are all connected. Electronegativity gives us a way to predict how atoms interact. Bond classification helps us determine whether electrons are shared or transferred. And bond polarity allows us to understand how charges are distributed within a molecule. From here, let's tackle 2 quick problems. This first question asks us to rank the following bonds in increasing polarity. We have a carbon-hydrogen bond, a nitrogen-hydrogen bond, an oxygen-hydrogen bond, a fluorine-hydrogen bond, and a carbon-fluorine bond. We're going to start by recalling the approximate electronegativity values. For carbon, the electronegativity is equal to 2.5. For nitrogen, it's 3. For oxygen, it's 3.5. For fluorine, it's 4. And for hydrogen, it's 2.1. Now we can go ahead and calculate the electronegativity difference for each bond. Let's start with carbon-hydrogen. This is going to be equal to 2.5 minus 2.1, which is equal to 0.4. Next, we want to do this for the nitrogen-hydrogen bond. This is equal to 3 minus 2.1, and that gives us 0.9. Third, we have our oxygen-hydrogen bond. This is going to be equal to 3.5 minus 2.1, and this is equal to 1.4. For our fluorine-hydrogen bond, this is going to be 4 minus 2.1, and that is equal to 1.9. Finally, we have our carbon-fluorine bond. This is going to be 4 minus 2.5, and that's equal to 1.5. Now, to rank them in increasing polarity, we want to arrange them from the smallest to the largest electronegativity difference. Our smallest electronegativity difference is going to be 0.4. That's associated with the carbon-hydrogen bond. Following that is the nitrogen-hydrogen bond. Following that is the oxygen-hydrogen bond. Then the carbon-fluorine bond. And then finally, the fluorine-hydrogen bond is the largest electronegativity difference. So again, this tells us that the carbon-hydrogen bond is the least polar, while the fluorine-hydrogen bond is the most polar among the given choices. Now for the second question, it asks which molecule has the least polar bonds. The choices are N2, H2, O2, or all the given options have equal polarity. To answer this, you need to recall that a nonpolar covalent bond can occur between 2 identical atoms bonded together. And when you have 2 identical atoms bonded together, the difference in electronegativity is going to be equal to 0. For example, for N2, the electronegativity value for nitrogen is equal to 3. So here we would do 3 minus 3, and that's equal to 0 because you have just a nitrogen bonded to a nitrogen. For H2, this is just a hydrogen bonded to a hydrogen. So the electronegativity difference is going to be 2.1 minus 2.1, and that's equal to 0. And the same concept applies to O2. So that means all three molecules are perfectly nonpolar with no dipole moment, and the electronegativity difference is equal to 0 for all three. So the correct answer for this second problem is going to be D. All of the given options have equal polarity. Now that we understand electronegativity and how it determines bond type, let's take a step back and look at why atoms form compounds in the first place. Atoms bond together because they want to achieve a more stable electron configuration, usually by filling their valence shell. This drive for stability is what leads to the formation of two major types of compounds: molecular compounds and ionic compounds. Molecular compounds or molecules, they consist of separate, distinct, electrically neutral groups of atoms that are held together by covalent bonds. These atoms share electrons, and there's no overall charge in the molecule. For example, water, H2O, sulfur dioxide, SO2, and hydrogen chloride, these are all molecular compounds where the atoms are bonded covalently, but they remain part of a well-defined separate unit. Ionic compounds, on the other hand, they consist of oppositely charged ions that are held together in a highly ordered 3D structure known as a crystal lattice. Instead of sharing electrons, like in molecular compounds, these substances form when a metal transfers electrons to a nonmetal, and that creates a positive ion, a cation, and a negative ion, an anion, that attract each other due to electrostatic forces. So examples of ionic compounds include sodium chloride, potassium bromide, and copper sulfide, for example. All of these form rigid crystalline structures due to the strong interactions and attractions between their ions. Now, to determine whether a substance is ionic or molecular, we can use a simple rule when we're looking at binary compounds. Binary compounds are compounds that are just made of two elements. If both elements are nonmetals, then the compound is molecular because nonmetals tend to share electrons rather than transfer them. Water is a great example. Hydrogen and oxygen are both nonmetals, so they form covalent bonds. But if one element is a metal and the other is a nonmetal, then the compound is ionic because metals tend to lose electrons while nonmetals gain them. For instance, sodium chloride. It consists of sodium, which is a metal, and chlorine, which is a nonmetal. Sodium donates an electron to chlorine, and it's going to form sodium cations and chloride anions that then arrange into a stable ionic lattice that looks something like this. Understanding this distinction is really important because molecular and ionic compounds, they have very different properties. In addition, now that we know how to classify compounds as ionic or molecular, we're ready to move forward and discuss how to name ionic compounds. Specifically, we want to learn how to name binary ionic compounds. Binary ionic compounds are made up of two elements. One is a metal and the other is a nonmetal. In the chemical formula, the metal is always written first, followed by the nonmetal. And this order reflects how the compounds form. Metals lose electrons to become positively charged cations, while nonmetals gain electrons to become negatively charged anions. When naming these compounds, we follow three key steps. The first step is that the cation is named first, and it's going to be named using the same name as the element. For example, sodium plus is simply called sodium in the compound name. Then the second step is that the anion, the nonmetal, is named second, but we modify the ending of the element's name by replacing it with IDE, ide. For Cl minus, we call it chloride instead of chlorine. Then our third and final rule is that no prefixes are used in ionic compound names. Those are reserved for molecular compounds, which we're not going to cover in this lecture. Let's take these three rules and let's apply them to a few examples. NaCl is called sodium chloride because it consists of sodium plus and Cl minus. Ki is potassium iodide because we have potassium plus, which we just referred to as potassium in the name, and I minus. So instead of saying iodine, we replace the ending with IDE, so iodide. Then we have here CaS, this is calcium sulfide, where calcium Ca2 plus and sulfide S2 minus form this ionic compound. Remember, we don't call it sulfur in the name. Instead, we replace the ending with IDE for the anion, so sulfide. Then we have Li3N. This is lithium nitride. Lithium is the cation. Nitrogen is the anion, but we replace the ending with IDE. So the name is lithium nitride. Then we have CSBr. This is cesium bromide. Cesium forms a cation. It loses one electron to form cesium plus. And bromine gains that electron to form bromine minus. We replace the ending with IDE, hence why we say bromide. And then finally, we have MgO. This is magnesium oxide. Magnesium loses 2 electrons to form a 2 plus cation, and oxygen gains those 2 electrons to form a 2 minus anion. We don't say oxygen, however, we want to replace the ending for the anion with IDE. Hence, the name of this ionic compound is magnesium oxide. Now let's try naming some new binary ionic compounds. For this first ionic compound, the cation is cesium plus. The cation is named first, and we use the same name as the element. So the first part of this name is going to be just cesium. Our anion is fluorine minus 1. When we are naming the anion, we want to modify the ending of the element's name by replacing it with IDE. So instead of fluorine, it's fluoride. The name of this ionic compound is cesium fluoride. We want to repeat this process for the ionic compound in part B. Our cation is aluminum 3 plus, so aluminum is the first part of the name, and the anion is Cl minus. Cl is chlorine. We're going to replace the ending with IDE, so it is chloride. The name of this ionic compound in full is aluminum chloride. Finally, for the ionic compound in part C, the cation is lithium plus, so the first part of the name is just lithium, and the anion is hydrogen minus. So we're going to replace the ending for hydrogen with IDE, so it's hydride. The name of this ionic compound is lithium hydride. Now that we've covered naming binary ionic compounds, let's extend this to compounds that contain polyatomic ions. Unlike monatomic ions, which consist of a single atom with a charge, polyatomic ions are groups of atoms that are covalently bonded together but still carry an overall charge. These ions act as a single unit in ionic compounds, meaning they do not get broken apart when naming the compound. Polyatomic ions have specific names that must be memorized to properly name compounds containing them. Here is a table full of polyatomic ions. If you are a student in my class watching this video, the polyatomic ions that you need to memorize for the course are the ones that are highlighted or dotted in orange. So we need to know ammonium is NH4+. We need to know that nitrite is NO2-, nitrate is NO3-, sulfite is SO3 2-, sulfate is SO4 2-, hydroxide is OH-, cyanide is CN-, phosphate is PO4 3-, carbonate is CO3 2-, hypochlorite is ClO-, chlorite is ClO2-, chlorate is ClO3-, and perchlorate is ClO4-. From here, when we're naming ionic compounds with polyatomic ions, we follow the same basic rules as before. The cation is named first, the anion is named second, but we don't need to change the ending to IDE if it is a polyatomic ion. Instead, we just use the name of the polyatomic ion as it is memorized. So let's apply this to some examples. Let's name this ionic compound first. In this ionic compound, sodium is the cation, so this is going to be the first part of the name, sodium. The second part of the name is in reference to the anion. The anion here is SO4. This is the sulfate ion. Since sulfate is a polyatomic ion, we keep its name unchanged. So the correct name is sodium sulfate. Let's do this one next. The cation here is potassium. The anion is this polyatomic ion that goes by the name perchlorate. Since perchlorate is a polyatomic ion, we keep its name unchanged. So the correct name here is potassium perchlorate. It's as easy as that. Now, so far, we've been working in one direction. We're taking a chemical formula and determining its name. But what if we're given the name of a compound and we need to figure out its chemical formula? The reverse process is just as important because it allows us to predict the correct ratios of ions in a compound based on their charges. To determine the formula of an ionic compound, we need to recall an important rule. Ionic compounds must be electrically neutral. That means that the total positive charge from the cations must exactly balance the negative charge from the anions. To systematically determine the correct chemical formula for an ionic compound, we need some background knowledge about how different elements form ions. Looking at the periodic table, we see a couple of important patterns. Group 1 metals always form +1 cations. That means they typically lose 1 electron. Group 2 metals always form +2 cations, so that means they lose 2 electrons. Group 13 metals, they typically form +3 cations, which means they lose 3 electrons. Then over here we have group 15. They form -3 anions, so they gain 3 electrons. Group 16 over here forms -2 anions, so they gain 2 electrons. And group 17 elements typically form -1 anions, which means they typically gain 1 electron. By following this pattern, we can pair cations with anions from the opposite side of the periodic table to form electrically neutral compounds. This means that when we are given the name of an ionic compound, the first step is to identify the charge of the cation and then identify the charge of the anion. Since ionic compounds must be neutral overall, we need to balance these charges by adjusting the ratio of cations to anions. In some cases, the charges already cancel out in a 1-to-1 ratio, like in sodium chloride. Sodium forms a +1 cation, and chloride forms a -1 anion. And here they combine in equal parts, +1 -1 equals 0. However, when the charges do not naturally balance, we need to adjust the number of each ion. So this could mean pairing 1 cation with 2 anions, or 3 cations with 2 anions, so on and so forth, depending on their charges. For example, let's consider calcium hydroxide. From the periodic table, we know that calcium always forms a 2+ cation, and we should have memorized that the hydroxide ion has a -1 charge. Since calcium contributes +2 and each hydroxide contributes -1, we need 2 hydroxide ions to balance out the charge. So the formula for a calcium hydroxide is CaOH2. Now that we understand the importance of charge balancing in ionic compounds, we can take a look at some common patterns that frequently appear in chemical formulas. The table here summarizes these trends by showing the typical ratios of cations to anions based on their charges. In this table, A represents the cation and B represents the anion. And the format here shows how many of each ion are needed to balance the charges and create a neutral compound. For example, when a +1 cation pairs with a -1 anion, the ratio is 1-to-1. For example, if sodium, which has a charge of +1, pairs with a chlorine, which forms a -1 anion, you only need one of each ion to pair up and create a neutral ionic compound. What about when you have a +2 cation that pairs with a -1 anion? In this case, you need 2 anions to balance the charge. An example is calcium chloride. Calcium forms 2+ cation. Chlorine forms a -1 anion. To balance this, you're going to need 2 chlorine atoms for each calcium cation. What if we have a +1 cation and a 2- anion? In this case, you're going to need 2 cations per 1 anion. An example of this is sodium oxide. Sodium forms a +1 cation. Oxygen forms a 2- anion. For this to form a neutral ionic compound, we're going to need 2 sodium cations for every oxide anion. Next, when you have a +3 cation with a -1 anion, you're going to need 3 anions per cation. So an example of this is aluminum chloride. Aluminum forms a 3+ cation. Chlorine forms a -1 anion. To balance the charge, we're going to need 3 chloride anions for 1 aluminum cation. If you have a +1 cation to a 3- anion, then in this case, you're going to need 3 cations per every anion. An example of this is sodium nitride. Sodium forms a +1 cation. Nitrogen forms a 3- anion. You will need 3 sodium cations to balance the charge of a single nitride anion. Then, if we have a 3+ cation paired up with a 2- anion, we're going to need 2 cations for every 3 anions. An example of this is aluminum oxide. Aluminum forms a 3+ cation. Oxide anions have a 2- charge. For 2 cations, we're going to need 3 anions. So aluminum oxide has the following formula, Al2O3. Lastly, when a 2 plus cation bonds with a 3 minus anion, you're going to need 3 cations for every 2 anions. So an example of this is calcium nitride. Calcium forms 2 plus cations. Nitride anions have a charge of 3 minus. Now, something that you can notice that will make this scenario and this scenario easy is that in order to balance the charges, you just swap the charges with the number of the other atom you have. So when you have calcium 2 plus and nitrogen 3 minus, to figure out how much of each cation and anion you need, you give that number to the opposite atom. So calcium 3, nitrogen 2. So with that, these charge balancing rules help us predict and write correct formulas for ionic compounds by ensuring that the total positive and negative charges cancel out to 0. Now let's apply this concept with a few examples, and let's write the correct formulas for lithium oxide and for magnesium fluoride. For lithium oxide, lithium forms a +1 cation, and oxygen forms a 2 minus anion. To balance the charge, we're going to need 2 lithium ions for every 1 oxide ion. And the way you can figure this out is you can just swap the charges here. So Li2O1. When there's a 1, you don't explicitly write it. So the formula for lithium oxide is Li2O. What about magnesium fluoride? Magnesium forms a 2 plus cation, and fluorine, it has a -1 charge. It forms a -1 anion. To balance the charge, we need 2 fluoride ions for every 1 magnesium ion. In other ways, you can do it by swapping the charges for numbers. So we need 1 magnesium and 2 fluoride ions. So the formula for magnesium fluoride is MgF2. Let's do some more practice problems so we can really perfect our skills in this. This first one says, which chloride has an incorrect molecular formula? We need to determine, okay, which of the given chloride compounds here does not follow the correct charge balancing rules. So in order to do that, we need to go through each option carefully. Let's start with calcium chloride here, CaCl2. Calcium forms 2 plus cations, and the chloride ions have a -1 charge. To balance this, we just swap these values to get Ca1, Cl2. Okay, that's exactly right. To balance this, we do need 2 chloride ions for every 1 calcium ion. So CaCl2 is absolutely correct. Let's move on to the next. We have sodium chloride. Sodium forms a +1 cation. Chlorine forms a -1 anion. If we swap the charges here, we get Na1Cl1. Remember, we don't explicitly write the ones. Since the charges are already balanced in a 1-to-1 ratio, NaCl is absolutely correct. Let's do the third one, Li2Cl. Lithium forms a +1 cation, and chlorine forms a -1 anion. Now here, if we switch the charges to figure out how much of each we need, we'll form LiCl. There is only 1 lithium to 1 chloride anion. So Li2Cl is actually incorrect. This doesn't follow our charge balancing rules. It's in fact the answer to this problem. But let's do the last one as well, MgCl2. Mg forms a 2 plus cation, and chlorine forms a -1 anion. If we switch these numbers, we get Mg1Cl2. This is the correct ionic formula for magnesium and chloride, and that matches this, so it is correct. The only one that has an incorrect molecular formula based off of our charge balancing rules is C. This should just be LiCl. In this next question, we're asked which oxide has a correct molecular formula. So we need to determine which of the given oxides is correctly written based on charge balancing. So again, we're going to analyze each option. Starting off with A, we have lithium oxide. Lithium has a +1 charge, and oxygen has a 2- charge. If we swap these values here, we get Li2O1. This is interesting. To balance the charge, we need 2 lithium cations for every 1 oxide ion, meaning that the correct formula should be Li2O. So this is incorrect. This is not the right answer. Let's look at the second one, NaO2. Sodium forms a +1 cation, oxygen forms a 2- anion. We swap these values here, we get Na2O1. That is the correct formula. That's not what we're given here. For this to be charge balance, we need 2 sodium cations for every 1 oxygen oxide anion. So the standard sodium oxide that follows charge balancing is going to be Na2O, not NaO2. So this is also incorrect. Let's look at the next option. We have K2O, potassium oxide. Potassium has a +1 charge. Oxygen has a 2- charge. If we swap these values, we get K2O1. So, to balance the charge, we need 2 potassium ions for every 1 oxide ion, meaning K2O is correct. This is a correct molecular formula. This is the correct answer to this problem. Let's still work through D. So here we have rubidium oxide. Rubidium typically forms a +1 cation, and again, oxygen forms a 2- anion. So if we go ahead and swap these charges, we would get Rb2O1. This would be the correct formula for rubidium oxide, but we're not given that here. The expected formula is rubidium-2O1, but that's not what we're given, so it's incorrect. The only correct molecular formula is answer choice C. Now that we've learned how to determine ionic formulas and understand their charge relationships, let's talk about lattice energy. This is going to be a really important concept in ionic bonding. Lattice energy is the energy stored in the bonds of a crystalline solid salt. It represents the strength of the electrostatic forces between the cations and anions in an ionic compound. The greater the lattice energy, the stronger the ionic bonds, meaning the compound is more stable and it has a higher melting point. A key factor that influences lattice energy is charge density, and this describes how much charge is packed into a given space. In fact, charge density is equal to the amount of charge divided by the size of the atom. From this, we can recognize that as charge increases, charge density also increases, and that leads to a higher lattice energy. And as atomic size decreases, charge density increases, and that also leads to higher lattice energy. Since charge density directly affects lattice energy, we can use these two facts to rank compounds based on their lattice energy. But how do we do that? Charge density calculations, they can actually get pretty complex. So we're going to simplify the process for this course into 2 key steps. First, we want to rank the salts by their total charge magnitude, since higher charge means higher lattice energy. Then, for the compounds with the same charge magnitude, We can then rank them by atomic size since smaller ions result in higher lattice energy. This is best understood with an example problem. So let's rank the lattice energy for the following compounds: aluminum oxide, calcium oxide, sodium chloride, and lithium chloride. The first step is to rank them by charge. How do we go about that? Well, let's start with aluminum oxide. Our aluminum cation has a 3+ charge, and our oxygen has a 2- charge. We want to multiply these two numbers together, forgetting the positive and negative sign. So it's just 3 times 2, that's equal to 6. Then we're going to do the same thing for calcium oxide. Calcium has a 2+ charge, and oxygen has a 2- charge. So 2 times 2 is equal to 4. For sodium chloride, our sodium cation has a +1 charge, and our chloride anion has a -1 charge. 1 times 1 is equal to 1. And then finally, we have lithium chloride. Lithium has a +1 charge, and chloride has a -1 charge. 1 times 1 is equal to 1. Now, since lattice energy increases with higher charge, we can already establish at least 2 of the rankings. Aluminum oxide is going to have the highest lattice energy, followed by calcium oxide. But what about sodium chloride and lithium chloride? They are tied for the total charge. So now we have to move into step 2, and we need to rank them by size. All right, so now we're comparing sodium chloride and lithium chloride's atomic sizes. Lithium is smaller than sodium. So that means the lithium ion has a higher charge density than the sodium ion. So that means lithium chloride is going to have a higher lattice energy than sodium chloride. So to repeat, aluminum oxide has the highest lattice energy, followed by calcium oxide, followed by lithium chloride, and then finally sodium chloride. And with that, we've completed everything we wanted to cover in this lecture. I hope that this has been helpful. Please let me know if you have any questions, comments, concerns down below. Other than that, good luck, happy studying, and have a beautiful, beautiful day.